Welcome to Understand the Math. In this Calculus 1 video, we're learning about the mean value theorem and how it connects the average rate of change of a function to its instantaneous rate of change. We'll start by reviewing Rolle's theorem, a special case of the mean value theorem, and then explore conditions for the mean value theorem to apply. Finally, we'll work through examples to find where the conclusion of the theorem holds and interpret what it means in real-world terms. Be sure to download the free guided notes to follow along and work through the examples with me. Let's start by learning about Rolle's theorem and see how it leads to the mean value theorem. Rolle's theorem is a special case of the mean value theorem, and it's easier to understand the mean value theorem after learning Rolle's theorem. I'm going to start with just a general idea of what Rolle's theorem is, and then we'll get into the mathematical definition. Rolle's theorem states that for any continuous and smooth function over an interval, if the function starts and ends at the same value, there's at least one point where the function's instantaneous rate of change is equal to 0. Let's now look at the mathematics behind Rolle's theorem, and I'll connect it to the graph that I have down here below. Rolle's theorem says let f be a function that satisfies the following three hypotheses. 1, f is continuous on the closed interval from a to b. 2, f is differentiable on the open interval from a to b. So notice it's continuous on the closed interval and differentiable on the open interval. That just means it doesn't have to be differentiable at the endpoints. And then number 3 tells us that f of a is equal to f of b. That just means that the function has the same value at both of the endpoints. Let's now jump down to our graph before we get to the conclusion of Rolle's theorem. Here's A and there's B. That's the interval that we're working with. And then we have f of A equal f of B. That just means that this point has the same y value as this point. Now let's jump to the conclusion. Going back up to the green box, it says there is a number C. This number right down here is on our graph in the open interval from A to B such that f prime at C is equal to 0. All that means that at C, the derivative is equal to 0 and the slope of the tangent line is horizontal. The reason that Rolle's theorem is a special case of the mean value theorem is because it's required that f of A is equal to f of B. In the mean value theorem, that requirement isn't there. Let me just put this theorem into a context that maybe you can understand, especially if you've ever been on a roller coaster. So imagine a roller coaster that starts and ends at the same height. Most roller coasters do. If the track is smooth and continuous, the coaster must reach a point in between where it's moving perfectly level, not climbing or descending. That just means that the slope of the tangent line of the track is equal to 0. This just means that the instantaneous rate of change, or the velocity at some point along the roller coaster ride, is equal to 0. We are going to look at some examples that involve the use of Rolle's theorem. Let's look at our first example. We are asked to verify that a function satisfies the three hypotheses of Rolle's theorem on the given interval. Then we are to find all numbers C that satisfy the conclusion of Rolle's theorem. The function f of x that we're given is x cubed minus 3x squared plus 2x plus 1, and the closed interval that we're given is from 0 to 2. I've graphed this function over here on the right, and when we get done with this problem, we're going to come back to that graph and see how our answers that we're going to get make sense. The first hypothesis of Rolle's theorem is that f is continuous on the closed interval from a to b. Our function f of x satisfies this because f of x is a polynomial, and all polynomials are continuous. So we say that f of x is a polynomial, so it is continuous on the closed interval from 0 to 2. Our second hypothesis says that f is differentiable on the open interval. Let's go ahead and let's take the derivative. F prime of x is 3x squared minus 6x plus 2. Notice that f prime of x is also a polynomial, so let's write that down. F prime of x is a polynomial. So we can conclude that it, meaning f of x, is differentiable. And here's where we have to be careful. It is differentiable on the open interval. It's always continuous on the closed interval and differentiable on an open interval. Let's now look at our third hypothesis. This says that f of a is equal to f of b. That just means the function is going to be the same value at the endpoints. So we are going to have to find the function at each endpoint. Our first endpoint, x is 0, so we're going to plug in x is equal to 0. And looking back up here, let me go ahead and highlight it so you can see where we're looking. We're going to substitute x is equal to 0 into that, and you can see that we get 1. Now we're going to do the same thing for x is equal to 2. This is going to be 2 cubed, which is 8, minus 3 times 2 squared, which is 4, plus 4 plus 1. Let's see. This is 13 minus 12, and it is equal to 1. So that hypothesis holds because the function has the same value at each endpoint. Now what we need to do is we want to find all numbers c that satisfy the conclusion of Rolle's theorem. And the conclusion of Rolle's theorem is that there is a point c between a and b where f prime at c is equal to 0. So what we have to do is we have to find the derivative, which we've actually already found in step 2, and we have to set it equal to 0. So let's just copy it down again. F prime of x is 3x squared minus 6x plus 2, and we set that equal to 0. Now, when I look at this, we need to factor it, but there is no way that we can factor that unless we use the quadratic formula. So let me just remind you what the quadratic formula is. I always think it helps to write it down. X is minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. Let's now apply that. We have x is equal to negative b, so that's a minus 6, plus or minus the square root of b squared, so that's minus 6 squared, minus 4 times a, which is 3, and then c, which is 2. And we divide all of this by 2 times a, which is 2 times 3. Let's now see what we get. This is 6 plus or minus the square root of 36 minus 24, all divided by 6. So this is 6 plus or minus the square root. Let's see, 36 minus 24, that is 12, all divided by 6. When we take the square root of 12, that's just the square root of 4 times 3. So we can pull out the 4 as a 2. And we get x is equal to 6 plus or minus 2 square root of 3 all divided by 6. So this is 1 plus or minus root 3 divided by 3. Now what we have to do is we have to determine if these points are in our interval from 0 to 2. Let's look at these individually. The first one is x is 1 plus root 3 over 3. Putting that into our calculator, we get approximately 1.577. That is between 0 and 2, so that one will work. Now let's look at the second one. X is 1 minus root 3 over 3. That is approximately 0.423. So that one also works. It is between 0 and 2. So we can write down that C is equal to 1 plus root 3 over 3, and C is equal to 1 minus root 3 over 3. Let's go ahead and let's highlight those answers. There's our first one, and there is our second one. So this tells us that at those 2 points, our function is going to have a slope of 0. Let's go back up to our graph at the top, and let's see if that's true. Let's first look at the value of our function at the endpoints. At 0, we have a function value of this, and here is our function value at 2. You can see that they are the same points. And then at this point, we have a horizontal tangent. And at this point, we have a horizontal tangent. This point is 1 minus root 3 over 3. And then this point over here is 1 plus root 3 over 3. I think it always helps to graph the function just so that you can really understand what it is you are calculating. I make all my graphs on Desmos. It's a free graphing calculator that is really easy to use, and I highly recommend it. Let's now look at our second example. We are given a function f of x is equal to 1 divided by x minus 1 quantity squared. We want to show that f of 0 is equal to f of 2. That is the third hypothesis of Rolle's theorem. But there is no number c in the open interval from 0 to 2 such that f prime of c is equal to 0. So we're going to show that. And then we have to answer the question, why does this not contradict Rolle's theorem? Let's start with the first part. I am going to begin by writing down our function. F of x is 1 all divided by x minus 1 quantity squared. And because we're eventually going to have to take the derivative, I'm also going to write this down as x minus 1 to the minus 2. Now let's look at our first part. We have to show that f of 0 is equal to f of 2. So let's plug in x is 0. This gives us 1 divided by 0 minus 1 squared, and that is 1. Now let's plug in x is 2. This is 1, all divided by 2 minus 1 squared. This is also 1. So we have shown that f of 0 is equal to f of 2. I have graphed our function over here on the right, and we can see the same thing. Here is f of 0, and here is f at 2, and you can see that they're the same value. Now what we want to show is that there is no number between 0 and 2 where the derivative is equal to 0. Let's go ahead and calculate our derivative. F prime of x is equal to minus 2 times x minus 1 to the minus 3 times the derivative of what's inside, which is just 1. Let's rewrite this as minus 2 all divided by x minus 1 quantity cubed. This is never equal to 0 because all we have is a -2 in our numerator. So there's no way this function can be equal to 0. Now we have to answer the question, why does this not contradict Rolle's theorem? The reason that it doesn't contradict Rolle's theorem is the first hypothesis of Rolle's theorem is that the function is continuous inside that interval. Notice from our function, let me go up here and highlight it. Let's look right up here. I'm highlighting it in pink. Notice that this function is not continuous when x is equal to 1, and 1 is between 0 and 2. You can also see this over here on the graph. There is actually a vertical tangent at x is equal to 1. So what we need to write down is that f of x is not continuous at x is equal to 1, so Rolle's theorem does not apply. Now that we understand Rolle's theorem, let's look at the mean value theorem and walk through some examples. The mean value theorem states that for any continuous and smooth function over an interval, there is at least one point where the function's instantaneous rate of change is exactly the same as the average rate of change across that interval. Let's now look at the formal definition of the mean value theorem. The mean value theorem says, let f be a function that satisfies the following two hypotheses. The first is that f is continuous on the closed interval from a to b. That is the same as Rolle's theorem. And then the second is that f is differentiable on the open interval from a to b. That is also the same as Rolle's theorem. What makes the mean value theorem different from Rolle's theorem is that there is no third hypothesis. There is no requirement that f of a has to be equal to f of b. Let's now look at the conclusion of Rolle's theorem and also look down here at our graph. In our graph, we have the endpoint on the left is a and the one on the right is b. And notice that f of a is different than f of b. Let's jump back up here to the green box. It says then there is a number c, here's our c right here, such that the derivative f prime at c is just f of b minus f of a all over b minus a. You might recognize that. That is equal to the slope of the secant line. So what the mean value theorem tells us that at some point c, the slope of the tangent line, that's right here, is equal to the slope of the secant line. That's the same thing as saying that the instantaneous rate of change is equal to the average rate of change. Let's now put this in context. Imagine you drive from one city to another on a smooth, continuous trip. The total distance and total time are going to tell you your average speed for the trip. For instance, if you drove 120 miles in 2 hours, then your average speed would be 60 miles an hour. The mean value theorem says that there must be at least one moment during your drive where your actual speed, that's the speed that is shown on your speedometer, is exactly equal to your average speed. So in other words, if you drove 120 miles in 2 hours, at some point during that trip, your speedometer, which measures the instantaneous velocity, had to have been 60 miles an hour at some point. We are going to walk through some examples that require the use of the mean value theorem. Let's look at our first example. We are asked to verify that the function satisfies the hypotheses of the mean value theorem on the given interval. Then we are asked to find all numbers C that satisfy the conclusion of the mean value theorem. The function f of x that we're given is x cubed plus x squared plus 1, and the closed interval is from -1 to 1. I put a graph of our function over here on the right, and we're going to look back at this graph after we finish all of our calculations. The first hypothesis of the mean value theorem is that our function is continuous on the closed interval. Our function, f of x, is a polynomial, so we can write down that f of x is a polynomial so it is continuous on the closed interval from -1 to 1. Every polynomial is continuous. Let's now look at the second hypothesis. F is differentiable on the open interval from a to b. It is a fact that all polynomials are differentiable, but let's just go ahead and take the derivative. We're going to need it later anyway. F prime of x is going to be equal to 3x squared plus 2x. Notice that the derivative is a polynomial, so we can say that f prime of x is a polynomial so f of x is differentiable on the open interval from -1 to 1. Now what we have to do is find all numbers C, here's C right here, that satisfy the conclusion of the mean value theorem. The conclusion tells us that the derivative at some point C is going to be f of b minus f of a over b minus a. That's just saying that the instantaneous rate of change, which is f prime of c, is equal to the average rate of change, which is the f of b minus f of a over b minus a. Let's start by writing down our function. We have f of x is x cubed plus x squared plus 1, and then we already found the derivative. That was 3x squared plus 2x. Now we're going to set the derivative, 3x squared plus 2x equal to f at 1 minus f at -1, all divided by 1 minus -1. We have lots of negatives going on there. Let's just go ahead and let's work on the right-hand side. F of 1 is going to be 1 plus 1 plus 1. And then we're going to subtract off f at -1. In case you're wondering, I'm looking right here for f of x. So this is going to be -1 plus 1 plus 1. And then we're going to divide all of this by 2. Let's see what this gives us. This is 3 minus 1 over 2, which is 2 over 2. So this actually is just equal to 1. We now need to solve the equation 3x squared plus 2x is equal to 1. Let's pull the 1 to the left, so we have 3x squared plus 2x minus 1 is 0. We can factor this. Let's see, we're going to put a 3x here and an x here. So this needs to be a plus 1, and that can be a -1. That works. So we end up with x is 1/3, and x is equal to -1. The conclusion of the mean value theorem says that f prime of c is f of b minus f of a over b minus a, but that is only valid in the open interval. So let's notice down here that this point is not in the open interval from -1 to 1. It is an endpoint. So this point will not work And this is the point that satisfies the mean value theorem. So our answer is going to be that C is equal to 1/3. Now let's take what we just found and let's go back up to our graph and see if it makes sense. Here is our function value at our left endpoint. That's at -1. And then at 1, let's see, it's up here. That is our function value at our right endpoint. And the mean value theorem tells us that the average rate of change, that's represented by the slope of the secant line, is equal at some point to the instantaneous rate of change. We found the point 1/3, and that's about right here. And you can see that the slope of the tangent line at that point is the same as the slope of the secant line. So the number C that we got is definitely correct. Let's now look at our second example. This is a classic example of how the mean value theorem can be used to find the bound on a function. I think this problem is always difficult for students because it never tells you to use the mean value theorem. You just have to know that you can use the mean value theorem to solve it. Suppose that f of 0 is -3 and the derivative is less than or equal to 5 for the closed interval from 0 to 2. We are asked to find how large can f of 2 possibly be. Let's go ahead and let's write down what we're given. We are told that f at 0 is -3. We are told that the derivative, f prime of x, is less than or equal to 5. And the interval that we're working with is from 0 to 2. And we want a bound on f at 2. We're going to use the mean value theorem to solve this. Let's start by writing down the conclusion of the mean value theorem. That conclusion is that at some point C, between A and B, the derivative at C is f of B minus f of A. Those are our endpoints, all divided by B minus A. It's just saying the instantaneous rate of change at some point C is equal to the average rate of change over the interval. Our A is going to be 0, and our B is going to be 2. And we know that f prime at C is less than or equal to 5, and that's because f prime of x is less than or equal to 5. Let's go ahead and let's plug these in. I'm going to go ahead and switch sides. So f of B is now f at 2. And we subtract f of A, which is f at 0. And then B minus A is 2 minus 0. And this is equal to f prime at C, which is less than or equal to 5. So we have f at 2 minus f at 0, all divided by 2 is less than or equal to 5. We want to find a bound on f of 2, so that's what we're going to solve for. F at 2 minus f at 0 is less than or equal to 10, just multiplying by 2. And then that tells us that f of 2 is less than or equal to 10 plus f at 0. We are told that f of 0 is -3. So we can say that f of 2 is less than or equal to 10 minus 3. So f of 2 is less than or equal to 7. So our answer is that f of 2 can be as large as 7. And that's it. You've learned the relationship between Rolle's theorem and the mean value theorem, how to verify that the conditions are met, and how to find the point where the instantaneous rate of change equals the average rate of change. To really master these theorems, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.